Hello, everyone. In this video, I'm going to talk about the properties of the Laplace transform. And as we know, we talked already about the linearity of Laplace transform, which makes it really good to work with. So for which is this one, Laplace transform of a sum is the sum of the Laplace transforms of these functions. Of course, if you have also a multiple, it's the multiple of Laplace transform of this function. So the new properties we're going to talk about is this first one here, which is called a translation in S. This one is a translation in S, means if you have a function times the exponential function to at, you can just do Laplace transform for s minus a. So, with the other notation, if it's just easy to see it this way with the input of s minus a. And these that I'm going to talk about are also considered, or they are theorems. So they're not something that we can doubt or something. They are proven to be correct. So they are theorems, so they are facts. And the proofs are also given in textbooks. And this one, it's easy to see because, Laplace transform's definition, you have that function of e to negative st. So if you multiply, you add exponents with this at here, and that's gonna, when you factor a negative, you'll see it, and it's just gonna give you directly this. All right. This is also another theorem. So this is also a powerful one because, as you see here, Laplace transform of a derivative. So this is Laplace transform of a derivative. It switches to Laplace transform of a function. And you see the S. So if you want to see all the details, of course, if f is continuous and sum 0 to infinity, and you have f prime to be piecewise continuous on 0 to infinity, so with both exponential order, then for some s greater than alpha, so all those details there, but this is a theorem when those conditions are met. You have Laplace transform of the first derivative is s times Laplace transform of the function minus f of 0. Right. All right, another theorem here. What if it's a second derivative? You can see the pattern here. So it switches to the function, which is also useful, but s squared. So that tells you that if I have the third derivative, which this comes in general, if I have the third derivative, then it's going to be here s cubed, right? So let's go back to this one, s squared times Laplace transform of a function minus s times f of 0 minus f prime of 0. So you can see the general solution here or pattern for this Laplace transform of higher order derivatives that you have s power n times Laplace transform of f minus s power n minus 1 times f of 0, and then n minus 2, and it keeps decreasing, and the derivatives order keeps increasing until you get to n minus 1. With of 0. All right, so what is this last one here? This last one is a derivative of Laplace transforms. It's also, but times t to power n. And here, in the proof of this one, an advanced calculus rule or Leibniz rule was used here. And it just says that if you have t power n, then you use -1 here, power n to the nth derivative with respect to s of Laplace transform of that. They are useful properties, and as I mentioned, they're also proven to be correct. And this is some from previous review, also a table of some common function that we use. If you have a function f of t, let's say sine of bt, then its Laplace transform is b over s squared plus b squared for some s being positive. Okay. And I'll explain more as we do, because I think the idea here, once we do the inverse and we solve a differential equation using Laplace transform, then the picture gets bigger. And then, of course, the appreciation of Laplace transform will come once we have this bigger picture. Because if you want to think about it for now, it's a transform that converts a function of a real variable here, kind of time, represented time, into a function of a complex variable s. So what it does is it will switch this kind of continuous uh, in a way a function, and of course there are some details we talked about piecewise continuous and stuff. From that domain of t to some s domain or s plane, which means it allows us to switch between the time domain and a frequency domain. So we'll see what this frequency means. And Laplace transform is going to have some significant operations, like of course, when it comes to differentiation and integration, it will just change them to like multiplication and division, and we'll see that, and we'll see when we get to convolution and stuff. But I think until next section, once you see inverse, then things will start. The picture or the puzzle will start to get better. All right, so in this video, I'm just going to talk about these properties, use them, but in the same time, kind of use this review here. All right, so let's do some examples. All right, so let's, of course, use the table here to find Laplace transform. So this function exponential to -2t times cosine 5t plus exponential to 6t minus 1. And of course, we know from the linearity is we can do these two here separately. Actually, there's 3 here terms separately. All right, so for this one here, A is -2 and B is 5. So when you look at the table to use, so here, refer back to the table, we're just going to have S plus 2. And this is where it's important to get used to this format. So when you want to do the inverse, you recognize what you have to switch. So as you see, I have S minus a -2, so plus 2 squared plus a 5 squared. Let's write it 5 squared. So remember now, when we have this form, we came up with this. So when we do the inverse, we need to kind of reverse it, just like you did with the previous operations and functions. All right, so this one is just going to be s minus a there. It was just a 6. And this, when we did this here, it was just 1 over s. All right, so we can go ahead and say s plus 2 over s plus 2 squared plus 25 plus 1 over s minus 6 minus 1 over s. That's, you see, it's not complicated. Since we already have a table, we have these formulas, so we can apply them. And we know how to do this as well if we want to use definition. All right, so if you run into, of course, something like this, you want to see what are the options that you have. Do I have something in the table that does this? Probably not. Then if I don't, then I will switch it back to kind of its component or its factors, then FOIL and all that. So I'll do here, I did it, so I'll just put what I came up with, but just to show you kind of, when you see the power doesn't necessarily mean there is a direct formula to use. Sometimes you have to adjust the function. All right, so each one now, based on linearity, each one is going to be by itself, right? So Laplace transform of this one plus the multiple you see here, Laplace transform of this plus 96 Laplace transform of this plus 256 Laplace transform of this plus Laplace transform of this constant. There is, of course, when you look at so in this, since we look like we have powers, right? And when you look at the table, Laplace transform for, let's say, this power function here, it's n factorial divided by s to power n plus 1. And yeah, so now for 4 factorial, 3 factorial, and times 16, 2 factorial times 96, right? Um, 1 times 256, then 256 times for a constant, it's 1 over s. And at the bottom here, you see 4. So 4 plus 1 is 5, and so forth. So that's the answer for that one. Let's do more. What if we have, let's say, let's try a constant with exponential. And let's do all squared. So same thing. So and just keep expanding. I think I'll just give you what I did towards the end, to expand this thing. All right. Then use the table, and you get 49 over s plus 14 over s minus minus 4, so s plus 4. And you get, what's 8? All right, so let's do one with exponential. Yeah, something different. Let's do NT. T exponential to 90 times, let's say, cosine 5t. All right. So here, and we'll apply the property. Which property we can use here? Let's say we have Yeah, so this is the one that has a t there. So t power n, negative 1 power n, first derivative of Laplace transform of a function. So what is the function here? Let's say this f of t, right? And of course on s, so yeah, it's going to be that. So let's use that. So we're going to use negative 1 power n, which is n is 1, right? But just to show, so it's first time used. Of course, on s. All right, so negative 1 power 1, first derivative with respect to s, Laplace transform of oh, so now you going to look at the table for this here, and you're going to substitute the answer, which is s minus 9, the a, and s minus 9 squared plus 5 squared from the b, which is 25. All right, so the table will give us this part. And here it's just a matter of finding the first derivative. We know how to do the first derivative of this. Pretend s is x, for example, x minus 9, and you differentiate with respect to x, doesn't matter. And then you have negative 1, you use. All right, so. And when you do that, you should get this. All right. Before we do cosine hyperbolic cosine, yeah, this one not just cosine, but hyperbolic cosine. I think we need to switch it to its uh, kind of equivalent form, which is this. Then that tells us based on the property that um, we got this. Which we can further separate if we want to these components. All right, so that gives us half. Again, here we're going to use the table to find Laplace transform of this function. So 1 over s minus b. It doesn't matter. We don't need a number, but we just use what's given. So this is plus ab. And now you can find the common denominator, which is 2 times s minus b times s plus b. So it looks like, s minus b times s plus b. That looks like s squared minus b squared. And you're going to do the top part, and you're going to get um, s squared minus b squared. 2s over these two cancel. S squared minus b squared. All right, so even something that looks challenging, it looks doable once we know this conversion. So let's do more examples that require this conversion, this type of conversions. Yeah, so for trigonometry, let's say we need Laplace transform of sine squared, let's say of 80. So here we're going to refer back to an identity that connects a sine square with uh, cosine 2x double angle. Yeah, so 1 minus cosine 2x over 2. Right? So if you need to refresh this one, it's you can solve for cosine of 2x when you see what it is. So here that's gonna be, let's put this 17 outside here. So sine square of 8 sine square of 80 will be 1 minus cosine of 8 times 2, right? It's 8 here, and it'd be 8 times 2 using that. Yeah, so 16t all over 2, which 17 now over 2 will go out. All right, and we have for 1, we know what it is. Laplace transform for a constant is 1 over s. And we know for cosine is just, let's go show it to you here. It's going to be this one here, right? So s over s squared plus b squared, and it's 6b here is 16. So so try it. You should get towards the end something like this. If you distribute 17 over 2. Doesn't matter, you can do different forms for this. But if you end up distributing, you get this type. All right, I think if we have cosine BT, it's good. Let's do one that's interesting as last one. Especially these don't show up as often, but I think it's good to review these. The product to sum to product, trig identities, they're not often used, but hard to memorize sometimes, but you can always come up with them if you know how to do, they're derived. But that's kind of the idea here. Is just when we see these, so when are we going to realize that's what the track to use? So you see these two are different. Since they are different, then maybe we have to go to that product some product thing identity there. And if you solve for sine of x, sine of y, you're gonna get cosine of x minus y minus cosine of x plus y over 2. So using this, um, that means just you're gonna have half outside, and you have cosine of 10 minus 2, which is 80, and 10 plus 2 is 12t. Then now you can do them separate. Once you do them a couple of times separate, then you know that you don't have to separate really to do just to each one. All right, so s over 2 times s squared plus 8 squared 64, and in a similar way here. All right, thank you.